Okay, my name is Obidebulaji Dennis, and I have with me.
Chloe McCarthy.
Yeah, we are going to present a project on the Block Arnoldi. We've divided the stuff into two parts. I will be talking about the Arnoldi built from a vector, while Chloe will be talking about the Arnoldi iteration built on Block Arnoldi. Okay, now if we have a block Arnoldi when we are given a variables, the M is the arbitrary number of rows and columns of the given matrix. We have A to be a matrix from a real matrix from M by M as a given matrix. We have N to be the number of subspace size that we can choose. We have a vector B. Then, very important, we are going to use our Krylov subspace to generate a tokenal basis and the H, which we call the upper Henselberg matrix. Okay, introduction. The Arnoldi process seeks to build an orthogonal basis Q from the Krylov subspace that span that expression we have there, which can be constructed a matrix H whose largest eigenvalues approximate. The most important fact here is that the matrix H built approximate the largest eigenvalue of the any matrix A. This time around, we are looking at any matrix A. It could be symmetric or a general matrix A. Okay, we have. Okay. Now, like in terms of the pseudocode, then we have how to build the vector Arnoldi. We are given a matrix A, and and also a vector B that is from Rm. So if you follow through that step, then we have it. Then this we implement a function as vector Arnoldi. If you look at it here, we just have to input, which is the size, the block size, and the matrix A. Then when we go through the code, we want to test our code. Then here we want to implement a real matrix of 128 by 128. Then want to compare the relative norms of the largest eigenvalues gotten from the given matrix A and the eigenvalue from our H matrix. I want to see how they actually are compared with each other. Okay. Now from there, we can see we are picking 20 iterations. Then we compare the numbers of metric vector multiplication for 20 iterations. Then the most important to note in this our presentation is the number of iteration, the convergence error, and the time it takes to have that convergence. We'll look at between 40. We have a better approximation to 10 raised to power negative 3 from 40 iterations, and if you go down to 50 iteration, we have the tolerance to be about 10 raised to power negative 4. And this column of that table is showing the time it takes for each iteration of eigenvalue to be computed. Now I'll hand over to Chloe to actually discuss the importance of building the block Arnoldi, and we'll compare the number of iteration, the time it takes, and the precision compared to vector Arnoldi. Chloe.
All right, so with Block Arnoldi, we're taking the Arnoldi process and trying to make it better, utilizing the fact that GPUs can compute matrix-matrix or matrix vector multiplications in parallel and then stitch back up the answer. This allows us to reduce our number of iterations by simply having more block size, which is simply more randomized vectors B. So for the Block Arnoldi, we are given a m by m real matrix. We're going to be using dense in our case, but note that this is meant for sparse matrices. We still see our positive results with dense matrices. But we will have a quote-unquote tall, skinny block vector matrix B, which is going to be m by d, where d is going to be our block size that we choose, and n the number of iterations. So, I will say that implies our subspace size is n times d. So note that we will lose the ability to converge past a certain point, and all that means is we will have a limitation that the number of iterations we have, n, multiplied by block size, d, must be less than or equal to our matrix A's row count or column count, m. Note for that this code, our number of iterations in the algorithm, it does one ahead of time. So we want to say that a script looking n, I'll call it italicized n, is going to be equal to our input n minus, or actually plus 1. My bad. I had those mixed around. Moving on, that implies that we'll see rapid divergence when n times d is greater than m. I will not show this, as the point of this is to show how much of an improvement this block algorithm can provide. So, to start, we will quit the kernel and run this code. And to give a quick scroll of the code, feel free to pause at any time. But really, I want to focus on the results. So this is up to your own interest to observe the code. So now, when it comes to showing the new plot of how the eigenvalues of H converge, we see that it tends to converge a lot faster. We have only 12 iterations here, and the top 8 eigenvalues are converged to. Meanwhile, up to vector Arnoldi, it took 50 iterations to converge 5 eigenvalues. Not optimal, comparatively. And so now we want to ask, what is the time saved with these iterations? Well, quitting the kernel to save computational resources, redefining our Block Arnoldi algorithm, we see, don't know why it does that, but we see with the table generated here, for a 128 by 128 dense real matrix A, 2 iterations with block size 64 yields a relative difference of 10 to the negative 15 magnitude. Again, up to the vector Arnoldi, 40 and 50 iterations was getting 10 to the negative 4 with 5/100ths of a second time. But this converges faster for about the same time, even less. Although we do get up to higher iteration counts, and that will increase the absolute time that it takes. But point is, if we meet our constraint, then we can reduce our iteration count for just having a large block size. And that is the benefit that transferring our problem to the block sizes yields over the vector. And that is the efficacy of Block Arnoldi.